Hello, complex analysis students. So today we're going to start talking about contours and contour integrals. This is very similar to the sort of thing you would have seen in multivariate calculus, where you would integrate a vector field across an arc of some kind. Almost exactly the same idea. So in some ways this may seem a little bit like review, but of course it's going to be done all in terms of, the language of complex variables. So we'll want to go back to square one on this. To start defining what we mean by a contour, we're going to start looking at functions of this kind, w mapping from the real line to the complex numbers. So you can sort of think about this as like embedding a straight line into the complex plane, and, to form an arc. So functions of this form will look like u of t plus I times v of t, where those component functions there, u of t and v of t, are just regular old real valued functions of one parameter. And like I said, typically these type of functions are going to describe some sort of a curve in the complex plane, or you might even think about it dynamically as describing the motion of a particle or something like that in 2 dimensions. And so, of course, when you want to talk about dynamics, you need to talk about derivatives. So the derivative of one of these type of curves, so w prime of t or dw dt, either way, would just be defined by taking the individual derivatives of the component function. So it'd be u prime of t plus I times v prime of t would be the derivative of w. And this, if you'll remember back to complex variables, this is exactly how you would have differentiated a curve back then, except you kept track of your curves as a ordered pair, whereas here it's still an ordered pair here too, but we used the I notation to keep track of the second component. Anyway, so for this first example here, if w of t is equal to cosine of t plus I sine of t, then that curve's derivative would be negative sine of t plus I times cosine of t, just differentiating those components separately. And similarly for the second example here, if w of t is t plus it squared, then that curve's derivative would be 1 plus I times 2t. Now you may recognize these curves if you think about them in terms of ordered pairs. The first curve there is just describing a unit circle centered at the origin, and the second curve there is describing sort of a standard parabola like y equals x squared. It's going to work out that these curves are actually going to be plugged into complex functions, and so we need to think about how to differentiate that composition where you're taking a curve and plugged it into a complex function. So for example here, if I put w of t into the squaring function, that's a complex function, right? Squaring. Then what you would expect when you differentiate that, you hope that you can use the chain rule, right? And of course you can. It'll just be 2 times w of t to the 1, and then multiply times the derivative of the inside, which is w prime of t. That's what you would expect that you'd, or hope that you can do. And let's verify that you actually can get away with that. The derivative with respect to t of this w of t squared, well, just put things in terms of the components. So w of t is u of t plus I v of t. You're going to square that. So that when you square that out, then your components are going to be u squared minus v squared, and your imaginary component is going to be 2uv. And I'm just dropping the of t notation. We understand that the variable is t for those functions. And now you differentiate this, and when you differentiate those individual components, we're just talking about regular old real valued functions, so you can use ordinary differentiation rules. And so that first derivative there for the real component, you're going to get 2u prime, using the chain rule, minus 2v prime, plus I, and then on the second component you need to use the product rule, so you'd get 2u prime v plus 2uv prime. And then from there you can actually work out, you can pull out at 2, and then with the stuff that remains you can actually see how it factors. You can see that it actually factors like this: u plus I times v times u prime plus I times v prime. So if you don't believe that, just multiply everything out and see that you don't get back what you had in the previous step. But then this is exactly 2, and then that u plus iv is w I'll put the of t back in there. And then the second part there is exactly the derivative of w, so w prime of t. So as advertised, it's sort of working like the chain you'd expect the chain rule to work, so that's good. Another example along these lines is, well, if you take the function w of t equals e to the z naught t, where that z naught is just a constant, this doesn't look like one of those functions where it's broken up, where it's expressed as a u component plus I times the v component. But you understand that, the exponential function, you can break it up into sines and cosines, right? And so it actually is a function of that type. And then what you would hope when you would differentiate this function e to the z naught t, well, this z naught t here is like an inside function. In fact, z naught t would just be the same thing as x naught t plus I times y naught times t. So you can see that that's a curve. It's a straight line, actually. And then that's plugged inside the exponential function, the complex valued exponential function. So it's just another chain rule situation. You're hoping that you should get z naught times e to the z naught t when you differentiate that. And in fact, you can verify that happens. And the way that would go is, okay, before you differentiate, you're going to take your e to the z naught t and express that as e to the x naught plus I times y naught times t. Then you can break that up a little bit into e to the x naught, e to the I y naught t. And now you can take the e to the I y naught t and break it up into cosine of that angle plus I sine times that angle, and you end up with e to the x naught. Then you'd have cosine of y naught t. Then you got plus I times e to the x naught sine of y naught t. And I'm still trying to take the derivative of that. I haven't taken the derivative yet, so let me put my derivative symbol out here. Okay, so now we can differentiate that. Just differentiate it component-wise. You have to use the product rule and the chain rule. So you'd get, let's see, differentiate the real component, you're going to get x naught e to the x naught t, multiply times cosine y naught of t, plus, then you got e to the x naught left alone, then multiply derivative of cosines, negative sine, so you get negative sine, well, negative y naught, sine of y naught t. Okay, so that's the derivative of the real component. Then differentiating the imaginary component is very similar. You get x naught e to the x naught t, sine of y naught t, and then this time plus y naught e to the x naught cosine of y naught t. And then you can convince yourself that this is actually x naught plus I times y naught multiplied times e to the x naught t cosine y naught t plus I times e to the x naught t sine of y naught t. If you don't believe it, just multiply it back out and see that you don't get exactly what you had in the previous step. And then that's z naught. And then the second bit is exactly the e to the x naught e to the I y naught t, which of course is z naught e to the z naught t, as advertised. All right. So derivatives are kind of working the way we'd hope when we plug a curve into a complex valued function. And in fact, we have there's a exercise that captures the version of the chain rule that we're hoping to have here. It says if your function f is analytic at the point z naught, which is w of t naught, and that point lies on some smooth curve. Well, we haven't defined what we mean by smooth, but we will pretty soon. But basically it just means that the derivative of the w of t function exists and is never equal to 0, or at least it's not 0 at the point in question. Then to differentiate f of w of t, so to differentiate this stuff here, it works just like you think the chain rule should work. You differentiate the outside function, leave the inside function alone, then multiply times the derivative of the inside function. So to be guaranteed that you can do that sort of thing, you need some certain hypotheses about derivatives of the functions involved, but that's not surprising. And it's not a super hard thing to prove. In fact, I'm going to make it a homework exercise, and it involves just using some facts about the facts you already know about derivatives and also Cauchy-Riemann. So yeah, we can see that for example, we could apply this fact directly to that example that we just previously worked out, where we broke it up into its component functions and differentiated it that way. So you really don't need to, because the inside function is what we call a smooth arc, and the outside function is the the complex exponential function, which we know is analytic on the entire complex plane. So it satisfies the hypotheses of this fact above, and of course then you do the derivative of the outside function is just e to the whatever is, the derivative of e to the whatever is e to the whatever, and then times the derivative of the inside function with respect to t is just z naught. So you do get the same result, just a lot quicker. Okay, the next thing we need to talk about are definite integrals of functions of this type that we've been looking at. These are not the kind of integrals that we're eventually going to do, but it's going to happen that the kind of integrals that we really want to do, so-called contour integrals, are going to boil down to doing this type of integral. So we need to do this first. It's sort of the simpler version. So if we've got a function, w of t equals u of t plus I v of t, the kind that we've been thinking about, if I want to integrate that function from a to b, you just integrate the individual components from a to b. So this would be integral from a to b of u of t dt plus I times the integral from a to b of v of t dt. So how would I compute something like that? Let's see an example. So if I want to integrate e to the it dt from 0 to pi over 4, well, first, before I start trying to integrate, let me break up e to the it as cosine t plus I sine of t. And then by definition, this breaks up into integral 0 to pi over 4 cosine t plus I times the integral from 0 to pi over 4 of the sine function. And those should be integrals that we can handle. So the first one there, the antiderivative of cosine is sine. Evaluate that from 0 to pi over 4 plus I, and then antiderivative of sine is negative cosine. We're going to evaluate that from 0 to pi over 4. And let's see, sine of t from evaluated from pi over 4 to 0, you'd get sine of pi over 4 is square root of 2 over 2, and sine of 0 is 0. Plus, then we have I times, you're going to have a negative square root of 2 over 2 when you plug in pi over 4 to cosine, and when you plug in 0, you get minus 1. So minus 1, so you get a plus 1. Yeah, I'll just leave it like that. One thing that can help us to evaluate these kind of integrals is a fundamental theorem of calculus for these kind of integrals. So the fundamental theorem of calculus for integrating these type of functions says, okay, suppose that the function that you want to integrate here is one of these functions, w of t equals u of t plus I v of t. And we have a second function of that form. Big W of t is big U of t plus I times big V of t. And we'll suppose that those are continuous on our interval. And the big W function is actually an antiderivative of little w of t. So if I differentiate big W, I get little w. That's our hypothesis here. So if we have an antiderivative for the function that we're trying to integrate, little w, then we can evaluate that integral simply by doing the antiderivative, big W, and then evaluate that from a to b like that. So in other words, it'd be big W of b minus big W of a. You should verify for yourself that this actually works. We get it from the fundamental theorem of calculus for single variable functions, just like you learned in calculus 2 maybe, or calculus 1. And the fact that that's the way we define integrals, integrals like this are broken up into two separate integrals that are real valued functions. So basically, this fundamental theorem of calculus is just saying, hey, you can do the fundamental theorem of calculus on each of the components and then put it back together into this thing, and it turns out to be an antiderivative. Check for yourself that fundamental theorem of calculus is as advertised. It does make calculating these sort of integrals a little easier when you see that you can apply it, when you see an antiderivative. Because, like for example, that function e to the it, I can just see, because I know how to integrate e to the constant times x from calculus 1, I can see that probably, the antiderivative has to be 1 over I e to the it, right? Well, sure. Just check real quick. If you differentiate 1 over I times e to the it, that you get e to the it. And also remember that 1 over I is the same as negative I. So I'm going to write that as negative I e to the it, 0 to pi over 4. And then I can just plug in the numbers. So you get negative I e to the I pi over 4. And then it'll be plus I times e to the 0. And so, that's negative I cosine of pi over 4, which is square root of 2 over 2, and then negative I times sine of pi over 4, so that'll be plus sine of pi over 4, which is square root of 2 over 2, and then that last term is plus 1, or plus I rather, plus I. So I see square root of 2 over 2 is the real part, and then plus I times negative square root of 2 over 2 plus 1. And that should match the answer that we got previously up here. Yeah, it matches. So being able to do the fundamental theorem of calculus just sort of saves you from having to break it up into components and doing two separate integrals. All right, so now we're going to have some definitions that pertain to different kinds of arcs. And so first of all, we need to define what we mean by an arc. Let's start with a function z of t equals x of t plus I y of t. So this is exactly the same kind of function we've been talking about, but we're just naming the component functions x of t and y of t instead of u and v like we did previously. But we've got a function like that defined on the interval a to b, and let's assume that the component functions x and y are continuous on the interval in question. And so if we take the set of points, c is just the set of all those z of t's, so it's just the points that function forms, we call that an arc. So to be an arc, you're just a function, like you're the output of a function of that form where the components are continuous. That's all. So it may not be differentiable. It could be very degenerate in some weird way, but it's at least continuous. And then we can sort of talk about special kinds of arcs. So we can talk about a simple arc. So an arc is a simple arc if it doesn't intersect itself. So i.e. what we mean by that is that for every t1 and t2 in the interval from a to b, t1 being not equal to t2 implies that z of t1 is not equal to z of t2. So that's a simple arc. And we can talk about what we call a simple closed arc. So we'll say C is a simple closed arc. Well, this just means that the terminal point and the initial point are equal to one another so that the arc is closed, but it's otherwise simple. So it doesn't have any other intersection points. And we also say that a curve C is positively oriented. We should say a simple closed arc is positively oriented. And this is going to be a kind of a bad definition for now. We could make it more precise later, but so positively oriented basically just means that if it goes in the counterclockwise direction. A little later we can define something called winding number that will tell you whether it's going in a sort of positive direction or in a negative direction. But for now, just intuitively speaking, like a simple closed arc is making, it's kind of like a circle is an example of a simple closed arc. And the circle, when you think about tracing the values of the points as t increases, it can either be going sort of counterclockwise or clockwise. And so if it's going counterclockwise, we consider that the positive direction. As an example, on the left picture here, we got the function z of t equals cosine of t plus I times sine of 2t. And when you trace out those points, it forms this figure 8 shape. And we would just say that's an arc. It's not simple because it has a self-intersection there in the middle. The picture in the middle is a simple arc. It's just taking two straight lines and putting them end to end. So the first straight line is this t plus it. So that takes you from the origin up to the point 2 plus 2i. And then starting from there, you go down on the other leg. But that's a simple arc right there because it doesn't self-intersect. And then the one on the right is a simple closed arc. That's just z of t equals e to the it. It's the unit circle centered at the origin. And you can see as you trace these points around the circle, as t increases, like you plug in t equals 0, then pi over 4, then pi over 2, you see that it traces out points counterclockwise around there. And so we'd say that that has positive orientation. It is possible to come up with a way to describe that same set of points on that circle, but in such a way that the points trace out in the reverse direction. In fact, if you just replace t with negative t, you'll get a circle with negative orientation. Some more definitions here. If the two component functions x of t and y of t are differentiable, so those derivatives exist and they're continuous, the derivatives, on the interval, then we say C is a differentiable arc. And when you have a differentiable arc, then when you look at this function, when you look at the magnitude function here of the derivative, because we're assuming that those derivatives x prime and y prime exist and they're continuous, then this composition, the square root of, x prime t squared plus y prime t squared, that's a continuous function. And if it's continuous, it's integrable. And when you integrate that expression, you end up with actually the arc length of the curve. So the arc length is just the integral from a to b of magnitude z prime of t dt. This is exactly the same formula you would have had for arc length back in multivariate calculus. That's why we like to have differentiable arcs, because we can always talk about the arc length for such curves. And in fact, you can always talk about what's called the arc length parameterization, and sometimes that's the very best parameterization of the curve that you can talk about it, just because it makes doing the calculus easier. If you've got a differentiable arc and the derivative is not equal to 0 for any of the points in your interval in question, then we call those kind of curves, smooth arcs. So one thing that's nice about a smooth arc is that when you look at the unit tangent vector, well, the unit tangent vector, just like it was back in multivariate calculus, it's just the derivative of the curve and then divided by the magnitude of the derivative. And we know we can divide by magnitude z prime of t because we're assuming we got a differentiable arc. So that's differentiable down there, but it's also not equal to 0 because we're talking about a smooth arc. So we're not dividing by 0. So this is well defined, that unit tangent vector. And also because of the continuity of the components of the derivative, this unit tangent sort of turns continuously as you go around the curve. So smooth arcs are where it's at. They have the nicest calculus. And then if you take a bunch of these smooth arcs and you put them together end to end, at least if you only put together a finite number of them, then the resulting thing is called a contour. Contours are the kinds of curves that we're going to be integrating along. So really it's smooth arcs that we want to integrate along, but it's okay if you stick together a few smooth arcs in a piecewise manner end to end. The calculus still works out pretty well. You just have to break up the integral into a finite number of separate integrals in those sort of cases. So now we've got defined the kinds of curves that we want to do our contour integration on. So let's see how that goes next. Oh, there is one thing that we're going to mention without proof. It's the so-called Jordan curve theorem. So it says if you got a simple closed contour, so we already know what simple and closed arcs are. Those are just curves kind of like a circle where it makes the initial point equals the terminal point, but it doesn't self-intersect anywhere else except for the fact that the endpoints are equal. If you have a curve like that and it's a contour, then that contour forms the boundary of two separate domains, one being sort of the inside of the curve shaded in yellow there in the picture that we call the interior. So that part's bounded, and then the second part is the part outside the curve, which we call the exterior, and that part's unbounded. So this seems kind of like an obvious sort of thing, like, well, yeah, of course a closed arc would do that sort of thing. But it turns out to be extremely difficult to prove, and we're not even going to try to do it here, but if you're interested in the proof of the Jordan curve theorem, I'm sure you can Google it and find it, but my recollection, I'm not even sure if I've seen the whole proof of it. Everybody always just says, that's hard, we're not going to do it in this class. I assume someone somewhere proved it. But anyway, we'll let that go without proof. So now we're ready to start talking about contour integrals. So of course we're going to start with a contour C that we have a parameterization for. So that just means we have a formula for it, right? Of course we're going to want to do things in such a way that our particular choice of representation of it doesn't matter. It really just matters what the domain is as a contour. But suppose we got a contour and we have a parameterization of it, z of t, and then suppose that we have a complex valued function f that has the property that when you compose it with the contour, you get a piecewise continuous function because the contour itself may be piecewise smooth, right? So if you have that sort of setup, then we can define the contour integral of the function f along the contour c as follows. So we're defining this notation down here in yellow. So that is going to be, by definition, the integral from a to b of f composed with z of t, And then dz is going to become z prime of t dt. You can kind of see that by thinking, okay, dz dt is z prime of t, right? So then multiply both sides of that by dt and you end up with dz equals z prime of t dt. So what's important to notice about this expression, this contour integral, is that that's the kind of integral that we previously talked about evaluating. This formula reduces the idea of a contour integral into something we know how to compute. So let me give you an example of how you compute it. So in our example here, our contour C will just be z of t equals e to the it, so that's your unit circle, but we're only going to consider the parameter t going from 0 to pi, so we're only getting the top half of the circle. Pictured it right over there. So I've got a contour. I can tell it's a contour because it's certainly differentiable, and you can check that the derivatives never equal to 0 on this interval, and so we're dealing with a nice contour. And so we're going to do the integral over that contour of the function just z. Very simple function, z. All right, so by definition, this integral would be integral. Well, since the parameter ran from 0 to pi, those are our limits of integration. Z along that contour becomes just z of t. So that's e to the it. So z became this. And then the dz part becomes the derivative of e to the it, which is I e to the it dt. So this part inside the integral dz became this. Okay, well, how would we compute that? How would we go further with it? Well, I see that, this is really just integral from 0 to pi of I times e to the, then you can add those exponents and you get 2it dt. And I think to myself, can I find an antiderivative for this function? Like, what would I differentiate to get I times e to the 2it? Well, I think you can see that it would just be 1/2 e to the 2it, and then we will evaluate that from 0 to pi. So check that this function right here, if you differentiate it with respect to t, that you get I times e to the 2it. I think that's pretty clear that that's what you get. And then you just plug in your limits of integration now. So we're just doing the fundamental theorem of calculus for these kind of functions. And you get 1/2 e to the 2 pi I, then minus, then you get 1/2, well, e to the 0. But you probably recognize that this is just 1/2 times 1, and minus 1/2 times 1. So we end up with 0. I guess it's worth mentioning, if you didn't recognize that you could have used the fundamental theorem of calculus there, you could certainly do this same integral without using the fundamental theorem of calculus. So you could do it like, well, it's the integral from 0 to pi. You'd have the same first step, just applying the definition of what a contour integral is. And then it would make sense to go ahead and write this as I times e to the 2it. But then you could express that as integral 0 to pi of I times cosine 2t minus, it'll be a minus because you're going to get an I times an I, and then you get sine times 2t. And so then this would work out to be integral 0 to pi of negative sine t dt plus I times the integral 0 to pi of cosine 2t. I forgot my 2 on the sign there. There we go. And you can do both of these integrals. Antiderivative of negative sine of 2t would be cosine of 2t. Evaluate that from 0 to pi. Plus I, and then antiderivative of cosine 2t would be sine 2t. Evaluate that from 0 to pi. And that first one evaluates out to cosine of 2t is, cosine of 2 pi is 1, then minus, then cosine of 0 is 1, plus, you get I times sine of 2 pi is 0, minus sine of 0 is 0, so it still works out to 0. So you could have totally done this problem by breaking it out into its component functions and then doing those two integrals separately. I think when you see that you can use the fundamental theorem of calculus, though, it's a little bit more straightforward, but in this particular case, it's such a simple function that you can do it fine either way. So now that you've seen an example of a contour integral, and you may not be feeling super confident about them, of course you need to work some examples before you start to feel comfortable with them. We'd certainly like to go through some of their properties. So the first one is that the value of the contour integral is invariant under reparametrization of the curve. So this just means that the curve C, it can have lots of algebraic descriptions, and it shouldn't matter which algebraic description of the curve you use. You should get the same answer for the integral each time. That's an important feature because the curve C is just a geometric object, and we don't want that object's geometry to be affected by just its description in terms of algebra. So to see how we get this invariance under reparametrization, let's suppose that we got a parametrization. This is z of t equals x of t plus iy of t, and in that case we're going to assume our variable little t is in the interval from a to b. Then a reparametrization of that curve would be something of the form where you take the original curve and you in place of t you have a function phi of tau that replaces t. So it's something that looks like this: big Z of tau equals little z of phi of tau, where tau is a different parameter that runs from alpha to beta. It'll be a valid reparametrization if that function that replaces t, what it really does is it maps the interval alpha to beta onto the interval a to b, and it has a continuous derivative on that interval alpha to beta, and its derivative is always positive. So this is all just a really long-winded way of saying that. It's a long-winded way of saying that we're replacing t by a different parameter, but we're not doing it in such a way that it really changes the geometry of the curve. So an example of this would be like, if you had e to the it, that's a parameterization of the circle on 0 to 2 pi. Well, what if you did something silly just like, hey, what if I just doubled the angle? So I do e to the I times 2t, but I'll call it tau. But then tau will run on 0 to pi. So that's just like going around the circle. It's the same circle, going in the same direction and everything. It just goes twice as fast. It's still the same circle though. So that's the sort of thing we're looking at for a reparametrization. And so to see why doing a reparametrization like that doesn't affect the value of the integral, let's just do a computation here. So at the bottom, I'm starting with the integral, the contour integral around C. I'm assuming C here is represented by that reparametrization, big Z of tau. So according to definition, this integral would go from, remember tau goes from alpha to beta, and then you do f, and then you replace little z with whatever the curve parametrization is. Well, we're doing big Z of tau inside of f, and then we got to multiply times dz, which would be z prime, big Z prime of tau, and then d tau. So then next, we're just going to substitute what we know big Z is at the top there. So this is f of little z of phi of tau, and then big Z prime, we'd have to use the chain rule that we talked about a little bit earlier. That becomes little z prime of phi of tau, multiply times the derivative of the inside function, phi prime of tau. Then we get d tau there. So at this point, we just make a u substitution like you would have done in calculus class. We say, hey, remember t? Let's set t equal to phi of tau, and then dt is equal to phi prime of tau d tau. And so that previous integral, if we change variables here, we end up with integral from a to b, because now we're doing t's, and it's going to be f of z of phi of tau, which is just t now, and then z prime of phi of tau becomes just z prime of t, and then the phi prime of tau d tau is exactly dt. So this is just dt here, but that's exactly the definition of the integral, the contour integral along C of f of z dz, if we were using if C was being parameterized by or C was represented by little z of t. We ended up with the same answer, but just represented by a different curve. So I realize that's a little bit heavy for you if you're not like super like, well reviewed on contour integrals from multivariate calculus. But the idea is pretty straightforward actually. So it's just saying if you represent the same curve in two different ways, you should get the same answer when you integrate. So just to give you a quick little example of how this would go, we've got two different parameterizations of the top half of the unit circle. So we're looking at our contour here, something like this. But on the one hand, I've got this representation of it here, let's say in blue. And then I've got this parameterization here, where all I'm doing is doubling the speed and doing it in half the amount of time, sort of thing. So if you do the integral along C using the first parameterization in blue there, it would be the integral from 0 to pi, and then z is e to the it, and dz is I e to the it dt. So this is the one we did a little while ago, and we got integral 0 to pi I e to the 2it dt. This is the one where we said, hey, we could do an antiderivative of 1/2 e to the 2it, evaluate that from 0 to pi, and we ended up with 0. Now if we use the second parameterization, the parameter tau runs from 0 to pi over 2, and then z in that case would be e to the I times 2 tau, and then dz would be 2I e to the I times 2 tau d tau, and we see that that's integral 0 to pi over 2. You've got constant 2I, and then e to the I times 4 tau when you add those exponents, d tau. And then you can do the same sort of thing, like what's an antiderivative of 2I times e to the I 4 tau? Well, that would be 1/2 e to the I times 4 tau, evaluated from 0 to pi over 2 this time. So just check that when you take this expression right here and you differentiate it, that you don't get that. It's an antiderivative, because when you bring the 4i down, the 2's cancel and you're left with 2i. And then of course when you plug in pi over 2, you end up with e to the 2 pi, so that ends up giving you 1/2. And then when you plug in 0, you get minus 1/2, so it ends up being 0 also. So you see the answers match here. So the calculation may look different, but you'll end up at the same result when you choose when you reparameterize the curve. Okay, so that's good to know. So here's some other properties that are kind of nice, not quite as technical as that last one. If you have a curve z of t and it represents your curve c, then if you negate the parameter t and then sort of reverse the order and negate the interval, kind of look at the negative of the interval, then you get a curve that we call negative c. So the difference between c and negative c is just that we think of them as sort of going in opposite directions. So c starts at z of a and works its way over to z of b, whereas z of negative t starts at z of b and then works its way over to z of a. So anytime you have a curve c, you can represent the negative of that curve, just the curve that goes in the opposite direction. It just reverses the endpoints, right? Like it reverses what we consider the initial point and what's the terminal point. And if you have two curves, let's say C1 goes from Z1 to Z2, and then C2 picks up at Z2 and goes to Z3, then if we just do C1 followed by C2, that's how we get what we call C1 plus C2. So the picture's over here where the arrow's pointing. So you see in red there is C1, and then C2 picks up where C1 left off. So you can combine those into a single contour, because remember, contours are just piecewise smooth, right? So here I'm just sort of doing a piecewise piecewise smooth curve by putting these two curves end to end. So that's the sum of two curves. Similarly, you can talk about C1 minus C2. The setup for that is that the two curves C1 and C2 have to have the same terminal point. So you see in the picture right over here, the red curve C1 points to that endpoint there in the middle, but C2 also points to that endpoint there in the middle. So if I do C1 minus C2, it forms the long curve that goes all the way across. So this curve, it goes from the initial point of C1 to the initial point of C2. And then a few other properties that you should be expecting about integrals, just linearity properties. So if you integrate on the contour C, z naught the constant times f of z, you can pull that z naught out. And if you've got the sum of two functions inside there that you're integrating, of course you can break that up. And these properties just fall out of how we defined integrals, right? If you go back to the definition of integral, you can chase that down. It's not like something you have to prove in terms of limits or something weird like that. It just comes out of the definitions. And if you integrate along the negative of the contour C, in other words, C sort of done in reverse direction, then that'll end up being negative the integral of f along C itself. We can prove that in a pretty straightforward way because we know how you form negative C. From at the top here, it just means you do z of negative t and then sort of reverse the interval. So if you have z of t equals x of t plus iy of t represents C, then we know z of negative t equals x of negative t plus y of negative t. And on the first one, z of t, I should probably say on the interval a to b. So this one's going to represent negative c on the interval from negative b to a. And so if you do integral from along negative c of f, that's going to be the integral from negative b to negative a, f of z of negative t. And then your dz, when you take the derivative of z of negative t, you pick up a negative. You'll get negative z prime of negative t dt. And then you could do something like, well, set u equal to negative t so that du equals negative dt. And then notice also that if t is equal to negative b, that gives you u is equal to positive b. And if t is equal to negative a, you get u is equal to positive a. So if you make that substitution, this integral becomes integral from positive b to positive a of f of z of u, and then the negative times the dt becomes du, and so you get z prime of u times du. So I just want you to notice that that negative in front of the z prime got absorbed by the negative, du equals negative dt. Lastly, you notice that the limits of integration are reversed of what they should be. We want a at the bottom. So you put a negative out front, you can reverse the order of integration here. So negative a to b, f of z of u times z prime of u du. Well, that's exactly the definition of negative integral along, the positive c of f of z dz. So anyway, it works out. And here's one last little property of contour integrals. If you're integrating along a contour that's the sum of two contours, of course we can do what you would hope you can do. This will work out to be the integral over the contour c1 of f of z plus the integral over the contour c2 of f of z dz. So this is useful whenever your contour has been, put together by stitching together a few curves with different formulas. That'll be handy. Let's do a few examples here just to sort of get some ideas under our thumbs here. So in the picture at the right here, I'm expressing the unit circle as a difference, C1, the curve in red on the top, which we'll find a parameterization for, and then minus the blue curve on the bottom, which is sort of the bottom half of the circle running in sort of reverse direction. But together, C1 minus C2 forms the whole circle. So if I wanted to do the integral of 1 over z dz, I know that going along C1, C1, that's just, let me write it over here somewhere. C1, I can just say that's e to the it on, where t is going from 0 to pi. So with that parameterization, the integral along C1 of 1 over z dz becomes integral from 0 to pi. 1 over z along that curve is 1 over e to the it. And then dz is I e to the it dt. Notice that those e to the it's cancel, and you end up with integral 0 to pi of just I dt, which is just pi I. Okay, now to do the second integral here, the integral along negative C2, I need a parameterization for negative C2. Either that or I need a parameterization for C2, and then I'll use my previous theorem that says, well, integral along negative C2 is negative integral of C2, 1 over z dz. Well, maybe it'd be easier to find a parameterization for C2 rather than negative C2, because I'm thinking, like, I could do e to the negative it on 0 to pi for just C2. C2 is already running in the, counterclockwise direction. I'm sorry, clockwise direction, the reverse direction. So if I put a negative on that t in the exponent, it just forces it to run backwards. So now this would be negative integral 0 to pi, and then along this curve, C2, z is equal to e to the negative it, and dz is equal to negative I e to the negative it dt, which is equal to negative integral 0 to pi of those e to the negative it's cancel, and you get negative I dt. So I get two negatives there actually canceling each other off, and so I just get, this will just equal pi times I. And now for the bottom integral, the integral along the whole curve C, which is really C1 minus C2, I could write that out as integral C1 minus C2, 1 over z dz. And then I could break that up as integral 1 over z dz along C1 plus integral along negative C2, 1 over z dz. And we already did both of these integrals separately above, and so we end up with pi I plus pi I, or 2 pi I. Now we didn't really have to get the integral along C of 1 over z dz, we didn't really need to break it up into these pieces. This is just an example to show you how you can break up a curve, or how a curve can be broken into several pieces and you can stitch them together to get a bigger integral. Here's an interesting example. So the setup here is I've got a curve C, and it's just any smooth arc that goes from this point Z1 to another point Z2. So I don't even care what the parameterization is, just let it be any smooth arc. So, maybe without specifying, anything too particular, let's just say that the curve C is represented by Z of t. Then the way this integral would go is you'd say, well, it's integral from A to B, because that's our interval down below. And then, Z just is Z of t. And then dz would be z prime of t dt. We do recognize that maybe you can find an antiderivative of that function that we're integrating there. And you can, because if you think about the function 1/2 z of t, if you differentiate 1/2 z of t, z squared of t. If you differentiate 1/2 z squared of t, or maybe I should write it this way, 1/2 z of t squared, like that. If you differentiate that function inside there, just notice that when you do differentiate that with respect to t, you get what was inside the integral. So that function's an antiderivative, and so I can use that fundamental theorem of calculus right? If you differentiated that, you'd bring the 2 down, it'd cancel that 1/2, then you'd get z of t raised to the 1, but then you got to multiply times the derivative of the inside function, which is z prime of t. So that's an antiderivative. And then I can use, I'm using the fundamental theorem of calculus here, and I get 1/2, and then z of b squared minus, then you get 1/2 z of a squared. Or if you want, you could just write this as z of b squared minus z of a squared over 2. What I would really want to point out about the answer, though, is that notice that it didn't really matter, the answer that we got didn't really matter what parameterization we chose, because the answer is just going to end up being the endpoints. So this is really z2 squared minus z1 squared over 2, where z1 and z2 are the initial point and terminal point of that curve. It didn't matter what curve was connecting those 2 points. The fact that we had an antiderivative meant that we didn't really have to consider the parameterization of that curve. So this is an example of what we call independence of path. As long as we chose a smooth arc, or even just it would also work for any contour, which is, piecewise smooth arc, the parameterization wouldn't matter. In fact, it's not just the parameterization, it's the curve itself. I mean, just any curve that goes from z1 to z2 would have the same answer. So that's what we mean by independence of path. And you can tell that the answer didn't depend on the particular path chosen because we were able to find the antiderivative. So being able to find the antiderivative is essentially what we mean by independence of path. Here will be a function where we won't have independence of path. So in this example, I've got 2 points that I'm focused on, the origin here, and then the point B. And I've got 2 different paths that go from O to B. The blue one goes first up from 0 to I at the point A, and then from A to B over. So it's like the 2 legs of the triangle, and then C2 is like the hypotenuse of the triangle. So if we had independence of path, I would expect if I integrated this function, f of z equals y minus x minus I times 3x squared, where z is equal to x plus iy. If I had independence of path, then it probably wouldn't matter if I integrated on the arc C2, or if I integrated on the arc C1, I should get the same answer. But here we're going to get 2 different answers. Let's do the arc C1 first, but C1's broken up into 2 bits, and so we're going to do its 2 separate bits first. So if we integrate on OA, that straight line segment, how do we get that? Well, the way that we integrate is we've got to have a parameterization, right? So I hope you recognize on OA here, here's a parameterization of it. 0 plus I times t, where t is in the interval from 0 to 1. So that's just going to change the y component from 0 to 1 steadily. So that means that your x is equal to 0 and your y is equal to t. And so f of z becomes, okay, now you're doing integral 0 to 1, and then your function f becomes y, which is 1, minus 0, I'm sorry, t minus 0, t minus 0 minus I, and then 3x squared is 3 times 0 squared, so that's just 0. And then you're integrating all that, and then you got to do dz. Well, dz, so your z of t is equal to, there's your z of t, right? Your 0 plus it. So z prime of t is just 0 plus I times 1. And so you end up with your dz is I, and then times dt. So let's sort of simplify this integral here. If I distribute that I get the integral from 0 to 1 of it, and then the other piece was 0. So this integral would be it squared over 2 evaluated from 0 to 1. So that's I over 2. And then you can do a similar sort of thing to integrate on the straight line AB. So there your function that you're integrating along would be t plus I. So the x coordinate's going to go from 0 to 1, but the y component just stays a steady I on that blue line, right? So you make the y component constant, and then so there here your x is equal to t, and your y is equal to I, and your dz is equal to 1 times dt. So let's see, you end up with the integral from 0 to 1, and then your f of z becomes y, which is I, minus x, which is t, minus I times 3t squared, because x is equal to t, remember? And then your dz is just 1 times dt. Oh, I see, I made a little mistake. My y function is not I in that example. My y function is 1. Your y is like whatever I times what, it's just the imaginary component, but it doesn't include the I itself. So that should be a 1 minus t there. So that changes things up a little bit. Let me fix it real quick. Yeah, so fixing it, we get integral 0 to 1, and then the real pieces 1 minus t dt, and then you'd have minus integral 0 to 1 3t squared dt. So you're going to get t minus t squared over 2 evaluated from 0 to 1 minus I times t cubed evaluated from 0 to 1. So that's going to work out to be 1 minus a half, which is a half, minus I. So 1/2 minus I. So then, to do the whole arc C1, remember that's the blue arc that consists of 2 pieces. So you just add those previous 2 pieces together, and you're going to get I over 2 plus 1/2 minus I. So what do you got here? I guess you could write that as 1/2 minus I over 2, or just 1 minus I over 2. So that's the integral along C1. So then next we're going to see if we get the same answer when we do the integral along the path C2. Now C2, we can just come up with a single parameterization for that. We don't need to break it up into pieces. So for C2, okay, so that's a line that basically goes from 0, 0 to 1, 1. So that parameterization, C2, would be just t plus it. And so your x is equal to t and your y is equal to t in that function. Now, and of course t is going to run from 0 to 1 here too. So remembering that that function is y minus x minus I times 3x squared. So y minus x is going to be t minus t, which is 0. And then it was I times 3x squared, so that's 3t squared. And then dz here is going to be 1 plus I, that's the derivative of z of t, and then times dt. So you get times 1 plus I times dt here. Oh, there was a minus in that f of z function, so this should be a minus right here in the middle. Okay, so this is just integral of negative 3t squared times 1 plus I. There's an I here too. Negative integral 0 to 1 of negative I times 3t squared, and that's all times dt. So I probably want to break this up into real and imaginary components. So that's integral 0 to 1. I'm going to end up with I'm going to have a 3t squared because that I times that negative I is going to give a positive 1, and then I'm going to have minus I times 3t squared, all that dt. So, I can just integrate the real part, and I get t cubed, 0 to 1, minus I, and then same thing on the imaginary component there, 0 to 1. So this is going to be 1 minus I. And so, anyway, notice these answers do not match. So here we do not have independence of path, because there we have 2 different paths. We're integrating the same function, the same f of z, going from the same initial point to the same terminal point, but we get 2 different answers. And that's essentially, we're going to see that, that function there, it's impossible to find an antiderivative for it. It's not the, that function up there is not the gradient of some other complex valued function. And you had a similar thing like this back in multivariate calculus. Okay, I think I'll stop there. Talk to you again soon. Bye.